everyone. Thank you all for coming this afternoon to our next speaker in the Wilkes Center Seminar Series. Incredibly excited to introduce Park Williams today. So Park got his bachelor's in earth system science from UC Irvine. Then he did an MA and a PhD in geography from UC Santa Barbara. After that, he's a postdoc at Los Alamos National Lab and a research scientist at Lamont Doherty Earth Observatory in Columbia. I think now Park is an associate professor in geography at UCLA. And what really stands out to me about Park and his science and his work over the years is he's an incredibly creative scientist, incredibly productive, and it's just amazing to see the scales he crosses in thinking about hydroclimate and fires and what climate change means for the Western US and around the world. His work's been recognized by a lot of different grants and awards, including the recent MacArthur Fellowship, and so we're excited to have him here. With that, welcome, Park.
Okay, thanks very much for coming. This is just such a nice opportunity to see what goes on at the Wilkes Center and to visit this university. Utah, it turns out, has played a fork in the road in my life a number of times. My first time to Utah was on a family road trip when I was 8 years old in the late 1980s, and it wasn't until that road trip that I realized I had a fascination with the natural environment. But seeing the sedimentary layers all over the Four Corners states as a young kid and trying to understand how the world would come to create such rock formations was kind of the beginning, or a huge fork in the road for me. And then it wasn't until almost 20 years later that I got the opportunity in my first year of grad school to attend Jim Ellringer's isotope camp here. And I spent 2 weeks here at the University of Utah, and that was a huge fork in the road. I don't do much isotopes today, but I had no idea what I was going to do in 2004 when I attended that camp. And one thing was clear to me, and that is if you want to do science with isotopes, to understand the environment, you can't just understand one thing. You need to understand the climate system, the living systems. You need to be very broad. And that is where it got impressed upon me that breadth is what I wanted. Today I take pride in not knowing what to call myself, and if any of you don't know what to call yourself, then I hope that one day you are proud of that as well, if you're not already. This talk is going to be about wildfire, and the reason why it is going to be about wildfire specifically in the Western United States is because there's been a very interesting trend over the last 40 years. If we look at the annual area burned in the Western United States, then we see that we've had an increase of over 200% since the early 1980s when high-quality satellite records allowed us to have high-confidence measurements in the annual area burned. And oftentimes when I show this figure or talk about the huge increases in annual area burned, people immediately think, oh, this is bad news, or this talk is going to be to learn why we are seeing such a destructive process go on. And so I just want to start the talk by making sure we're all on the same page and demonstrating that I understand that fire is not inherently a bad thing. Fire has been on the continents for as long as plants have been on the continents, for hundreds of millions of years. If you walk around any old growth forest in the Western United States, then you'll see evidence of fire everywhere you look. If you know what you're looking at, this tree might be 2,000 years old, and this is just very likely the largest and most recent of the fire scars. Very likely this tree has survived tens or even hundreds of fires during its life. Fires in many forest ecosystems provide all kinds of benefits to the ecosystem, such as clearing out the understory, reducing competition, and keeping forest densities in many forest ecosystems light enough in order to prevent catastrophic crown fires. But crown fires are also common in some parts of the Western United States, and those fires are not necessarily bad either. For example, the lodgepole pine in the northern Rockies really relies on crown fires in order to reproduce. But people are increasingly in harm's way, and this is why fire is why the increase in wildfire is such a difficult thing to deal with. People are either are often physically in harm's way, but more often people are remotely in harm's way. The way that wildfire affects most of us across the United States is not because the flames are putting us or our property in danger, but it's because the smoke is putting us in danger. After fire, or fire can have profound influences on hydrology in a region. After big forest fires, stream flow can often increase. That could be a good thing in water-limited systems, like people in the southwestern United States, but water is only good if you're expecting it. Wildfires can also loosen up topsoil and promote flooding and mudslides, as we were reminded of in this catastrophic event in 2018 in Montecito, California. And even though fire is a natural process and ecosystems have evolved to deal with fire or even rely on fire, the fires that we're seeing today are not always good for ecosystems. In the southwestern United States, for example, ponderosa pine forests is a forest type that is not very good at spreading seeds long distances. Here we're looking at a picture of the aftermath of the Las Conchas fire that took place in the spring and summer of 2011 in northern New Mexico in the Jemez Mountains. This fire opened up gigantic gaps in a dense ponderosa pine forest. Squinting at this image, it'll be hard to find a single living tree, and that means in the middle of this image, this landscape is very far away from the nearest seed source. And so even if climate became ideal for ponderosa pine to recolonize this area, it could take hundreds or even thousands of years for the entire area to be recolonized by ponderosa pine. The existence of ponderosa pine in this area then suggests that very likely this type of fire is not the type of fire that was occurring all that regularly over the millennia that preceded the current era. And so whether or not fire and an increase in fire in the western United States is a good thing is really a matter of perspective. But if we look at this plot, where the red I'm showing you the same time series I showed you, annual acreage burned, and then the green is the amount of money we spend fighting fires in the United States as a whole, then what we can see just from the way that we spend our own resources is that humans overall don't seem to like fire. And as I'll show later, in the 1800s and the preceding centuries, large fires were much more common than they've been over the last 40 years, even much more common than they've been in the last decade. However, the difference, or why it's concerning that we have this rapid increase in wildfire today, is because it's clear from the green time series that this increase in fire activity is occurring despite our best efforts to control it. We controlled wildfire in the western United States for the better part of a century. Today, even though we acknowledge that trying to control every single wildfire probably was not a very good idea ecologically, we still do try and put out essentially every single fire as soon as it gets lit. And this increase that we're seeing is in spite of our best efforts to see it not happen. So this talk is going to start by trying to address the question of why have we lost control of wildfire despite our best efforts? And so to zoom in on the answer, we'll first look, we'll just split the western United States into two regions. One is the forested region and one is the non-forested region. And I'm showing you now the annual acreage burned on the left in forested areas and the annual acreage burned on the right in non-forested areas. You can see that we've seen an increase in annual area burned in both parts of the western United States, but the explosion of fire activity has really been dominated by an explosion of the sizes of forest fires. 2020 nearly doubled the previous modern record, and then 2020 came very close. It would not surprise me at all if in the next decade we see this record that was set in 2020 beat again by 50 or even 100%. Sometimes we hear people speculating about why the annual acreage burned is increasing so quickly, and they'll say, oh, the reason is because it's getting warmer and therefore the shoulder seasons of the fire season are seeing more fire. So spring is seeing more fire and fall is seeing more fire. And that is the case a little bit. But the increase in area burned is being dominated actually by fires in the heart of the fire season, the summertime in the western United States. This is the case in forested regions and non-forested regions. And so even though things like melting of snowpack in the spring may promote more spring fires, or increases in human population might promote more spring fires in some places, if we want to understand why we have lost control of wildfire in the western United States, we really need to understand why we've lost control of wildfire during the heart of the wildfire season, specifically in forests. And it turns out that the increase in annual area burned is actually dominated by a very rapid increase in the very largest fires. So in this set of plots here, I'm showing you the magnitude of annual area burn trends for 10 different fire size classes. Here we're looking at the trend in annual area burned by each year's smallest 10% of fires. Over here we're looking at the increase in annual area burned in each year's largest 10% of fires. The largest 10% of fires in forested areas account for 70% of the observed increase in forest area burned. We see a similar pattern in non-forested fires. I'll show later that it actually isn't a change in the number of fires that we've seen in the Western United States. It's all, the entire increase in area burned is being driven by an increase in the size of the average fire. And the size of the average fire is increasing because of very rapid exponential growth of the size of the largest fires. So it's actually a pretty small number of fires that's driving this huge increase in area burned. That becomes relevant when if we start thinking about solutions. If we were to want to stop the annual area burn from increasing so fast, then we're actually talking about trying to stop the very largest fires that are inherently large because they are very difficult to put out. They're being driven by extreme weather conditions. They're often moving through very dense fuel types. We're talking about if we want to manage to slow the increase in size of fire, we need to be talking about or thinking about how we address the growth of the largest fires. As I'll say later in this talk, fire size probably is not the most important variable to focus on. At the end of the talk, I'll talk a little bit about other variables, but most of this talk does focus on annual area burned. The reason for that is because annual area burned is something that's measured really accurately, and it also correlates really well with the variables that we think should be predictors of fire. So a lot of the talk focuses on annual area burned, even though I acknowledge that's not the most meaningful variable in terms of ecosystems, carbon, or people. So why are fires getting larger so rapidly? In trying to address this question, there are three things that we should think about. One are fuels, one is the dryness of fuels, and one is the ignitions of fires. And so we'll just start by talking about dryness, and I'll get right to the punchline, and that is that the annual area burned in Western United States forests correlates exceptionally well with drought. And specifically, or the variable that it tends to correlate the most strongly with, is this variable here, the vapor pressure deficit. The vapor pressure deficit you can think of qualitatively as the sponginess of the atmosphere, the thirst of the atmosphere. What it is technically is the difference between the total amount of water vapor that the atmosphere could possibly accommodate at its given temperature minus the total amount of water vapor actually in the atmosphere. So it's kind of like, if you think about the atmosphere as this vacuum that's always trying to pull moisture out of soils and out of ecosystems. The higher the vapor pressure deficit, because of heat and lack of humidity, then the thirstier the atmosphere, the faster the atmosphere is going to dry out vegetation. Each dot here represents a year from 1984 to 2023, and the vertical axis is the total forest area burned. The horizontal axis is the March through October average vapor pressure deficit. And what you can clearly see is that if it's hot and dry, so that making vapor pressure deficit high, these are years that are reliably very high burned area years in our forested areas. And when it's cool and humid, then we have very likely low area burn. The difference in colors is really important. Blue is representing years in the 1900s. Red is representing years in the 2000s. And so what this plot is implying is that as the climate became warmer and drier over the last 40 years, then the annual area burned crept up this regression line just the way that we would have predicted it would if I'd made this graph back in 1999 and only known that it was very likely going to get warmer and drier in the next 20 years. Very importantly, you may be noticing that this vertical axis here is actually plotted as a log scale. The reason why I plotted as a log scale is to demonstrate just how stable and reliable this relationship has been over the last 40 years. But if I take it off of the log scale, then it's clear that this is actually a strong exponential relationship. Over the last 40 years, each bit of warming and drying has led to more of an increase in forest area burned than the previous bit of warming and drying. This is why it's this exponential shape of this plot that explains why we don't see records in area burn just gradually beat, but instead we see records in area burn get shattered. Because as we know after living through a pandemic, exponential processes, even if they seem benign at the beginning, can have the potential to drive things out of control. And it's this exponential response that I believe of forest fire area, the sizes of the largest forest fires specifically, to warming and drying that has caused us to lose control of the fire regime in the western United States. But wildfire must be affected by more than just the dryness of fuels. It certainly must be affected by fuel types as well. We can reason our way through this very easily if we just imagine or look at these two different ecosystems, both in California, only 100 or 200 miles apart, and just ask yourself, if we were to warm and dry out both of these ecosystems and light a flame and provide some wind, which one is going to lead to the larger, more energetic fire? It is very likely the forested ecosystem. There is way more fuel available here to spread a huge fire than there is here in this desert ecosystem. The difference, or the reason why this ecosystem isn't burning every year, is because most years the fuels are too wet to burn. But if we dry the fuels out and add a spark on a windy, hot day, we're very likely to get a large fire spreading very rapidly here, whereas every year in this desert ecosystem, the fuels are very likely dry enough to support fire, but they're not usually abundant enough to support large, fast-moving fires. And so how does this square with what I just said about climate trends really driving the trend in annual area burn? Well, I'll go back now and show you the same scatter plot for forest fire that I did a second ago. In forests, where fuels are generally not a limiting factor for fire growth, then the hotness and the dryness of the atmosphere is a very good predictor of how much is going to burn in a given year. If we step outside of forests, though, and do the same exact analysis, we see a tendency for the hottest and driest years to be big fire years. But there's a whole lot more going on that complicates this relationship. For example, outside of forests, and specifically in desert ecosystems or grasslands, the way that a hot and dry year can most easily promote a big fire year is if the prior year was wet. The prior year being wet helps to grow new grasses. Those grasses, if they dry out in a subsequent hot and dry year, will then be available to spread fire more easily. People also live much more often outside of forests than inside of forests. People are providers of many ignitions outside of forests, and people are very good at putting out fires. And so people are constantly working, or very effective at complicating the relationship between climate and fire outside of forests, whereas in forests, it appears that no matter what we people do, at the end of the day, the amount of acreage burned is very, very sensitive to what the climate was. So how do these two concepts square? If you are in forested areas, all it takes is warming and drying to increase fire activity, and so as we've warmed and dried the environment, we've seen forest fire activity explode. But we also know from the previous slide that the more available fuels are, then the more likely fires are, or the more able fires are to respond to warming and drying. Here we're looking at two snapshots of the Yosemite Valley, about 110 years apart. And the big difference between these two scenes, 110 years apart, is that the forest ecosystem is much more heterogeneous. The vegetation ecosystem in general is much more heterogeneous. The fuel loads 110 years ago are much lighter than they were in 2011. And a main reason for this is because of fire suppression. In the late 1800s, early 1900s, we began to take control of the fire regime in the western United States, preventing forest fires very successfully, and as a result, more fuels were able to accumulate over time. And so now if we ask ourselves, if we were to warm and dry this environment with human-caused climate change versus warm and dry this environment with human-caused climate change, which environment is more likely to support an increase in fire activity because of the warming and drying? And it's not just in Yosemite that we have dramatically changed the fire regime. Fire scars embedded in tree rings tell us that for hundreds of years prior to the late 1800s, fires were very common across many of the forest types in the western United States, across the Southwest, Many forest areas in the Sierra Nevada, many forest areas were experiencing fires every 5 to 20 years. And then consistently we see in the late 1800s, the fire scars disappear from our cross sections of tree ring records. We are very lucky in Western North America to have a whole load of data from tree ring records on the occurrence of fires. Each of these red dots is showing you the location where we have data of fire scars from tree rings. We know the exact years the fires burned through the forests in these areas with the red dots. Here in the blue time series, I'm just showing you every year the percent of the sites in this fire scar network that recorded fire scars. And so you can see that from the beginning of the data set in 1600 until the late 1800s, fires were very common in these sites, and then beginning in the late 1800s, fires started disappearing. This is because humans, for a long time, or for over 100 years, took control of the fire regime first by expanding grazing across the western United States, animals munching up grasses, causing fires to not spread as easily, and then through the very effective fighting of fire. And so I think in much of the western United States forested area, both of these things have been very important. Warming and drying of the environment is what has dominated the trend in annual area burn. But if we had not been fighting fires so successfully for the last century and allowing forest biomass to accumulate as much as we did over the last century, then very likely the same global warming event that we've seen over the last 40 years would have been less effective in driving an increase in area burn. Very likely still would have seen a large increase in forest area burned, but it probably would not have been as strong, and a record-breaking hot summer wouldn't as easily translate into a record-breaking wildfire summer. So how about people? We have people living all over the West. Between 1990 and 2010, the population of the western United States increased by something like 36%. And in the so-called wildland-urban interface, where people are living very close to flammable vegetation, the population increased by over 50%. So people have been disproportionately moving into flammable areas. People light a lot of fires. If you look across the entire the entire continental U.S., something like 85% of all wildfires are ignited by people or the equipment that people are responsible for. In the western United States forested areas, it's more like 50% of fires are set by people, and so people are very good sources or very efficient sources of fire. So it would make sense to theorize that the increase in population, especially in flammable areas, would have also contributed to the increase in wildfire activity. But that's actually not what we see. If the increase in population was causing an increase in the ignition of large fires, then we should see increases in the frequency of large fires. In forested areas, we do see a bit of an increase, 67%, but that's nothing like the 1,000% increase in annual area burned that we've observed. And outside of forests, then the annual frequency of large fires has not changed at all. And this doesn't just go for large fires. If we look at all fires, and we even split up fires caused by lightning versus fires caused by humans, we see, now this data set only goes back to 1992 because we don't have data on the causes of fires prior to 1992, but from 1992 to 2020, we see in forested areas that the increase that we saw on the previous slide in the frequency of fires is actually being driven by lightning, and that human-caused fires are actually on the decline. If we step outside of the forests, where people are more often living and people are better at getting to fires and suppressing them, then we see that human-caused fires have actually been plummeting in frequency. In California, this is actually really extreme. The human-caused fire frequency has decreased by something like 70% in California since 1992. So, long story short, even though people have accumulated on the landscape and people are good at starting fires, people are even better at putting out fires, and people are not responsible for the huge increase in annual area burn. Now, that's not to say that humans are not responsible for lighting some of the most destructive fires. The Camp Fire that burned down Paradise, California a few years ago was set by human infrastructure, a power line that went down. So if people were not on the landscape, that fire wouldn't have occurred. But if we zoom out to the scale of the western United States, it is the warming and drying of the environment and very likely combined with artificially dense fuels in many western United States forests that's responsible for us having lost control of wildfire in the western United States. So what's going to happen in the future? We know that large fires are promoted by warmth and aridity. We can use the March through October vapor pressure deficit as one proxy for fire danger. Here we're looking at a time series in black of the observed vapor pressure deficit record, and then in red here is the CMIP-6 multi-model mean projection of future vapor pressure deficit trends under a very aggressive emission scenario, the so-called SSP 585 emission scenario, which I hope is being increasingly thought of as a worst-case scenario, or even very unlikely scenario where we burn essentially all the coal we can get our hands on. In blue is a more moderate emission scenario where CO2 accumulation in the atmosphere begins stabilizing by the middle of this century. And you see by the end of this century, we're looking at two very different worlds. But in both cases, by the middle of this century, in the 2050s to 2070s, the average year is projected to have a vapor pressure deficit about as high as the record-setting years that we've seen recently that coincided with huge annual forest areas burned. Vapor pressure deficit is not the only variable that's important to fire. Other variables are important as well. Clearly, precipitation must be important. Correlation analyses indicate that the frequency of summertime precipitation days is actually really important to wildfire. The years with extremely infrequent precipitation days promote more area burned. In black, we're looking at the observed record of wet day frequency in the western United States forest area. You can see quite a big trend over the last 40 years. Not such a big trend over the last 80 years or so. What do climate models say is going to happen to the frequency of wet days? Well, climate models say that on average, we might see a decline in the frequency of wet days. But more importantly, climate models also project an increase in the year-to-year variability in the frequency of summertime wet days. And so even though the average doesn't go down that much, the extremely dry summers become much more frequent. In both of these scenarios, the frequency of extremely dry summers almost doubles the historical frequency. And so from both of these perspectives, from the perspective of atmospheric thirst and the perspective of precipitation supply delivered from the atmosphere, models are suggesting that the future is going to continue to be more conducive for large forest fires than the historical period. This suggests qualitatively that we should expect the increase in annual area burned to continue. But it would not be smart to simply extrapolate out the relationship that I showed you earlier between annual area burned and vapor pressure deficit out to the end of this century. Just for fun, I've done that. Each of these dots here shows you the CMIP-6 multi-model mean vapor pressure deficit projected for each decade from the 2030s out to the 2090s. And then the whiskers around those dots bound the different, all the projections from all of the, I think, 27 CMIP-6 models that I considered. If we were to believe that the relationship between annual area burned in the forests of the western United States and the vapor pressure deficit was going to remain consistent for the rest of the century, then what that means is by the end of this century, we end up with decades when the average year has over twice the annual area burned as the current record-breaking 2020 year, and very likely we have sequences of years where more than 10% of all of the forest area burns in a given year. That is very likely not realistic. And the reason is because vegetation is a dynamic thing. When fire burns through a forest or burns through an ecosystem, then everything changes. This picture of the aftermath of the Yellowstone fires in the late 1980s, as this map shows, if a new fire would have burned through this area the next year, then very likely that fire behavior would have been different from the previous one. Fire affects forests, or fire affects fuels, and those changes in fuels feed back to affect forests. If we want to understand what the future of forest fire looks like in the western United States, we need to understand really complicated processes like succession after a fire. What's going to come back? How fast is it going to take to come back? How fast is it going to grow Will anything come back at all? Here we're looking at two very different post-fire processes, succession of lodgepole pine here after the 10 years after the Yellowstone fires, and here we're looking at a picture I took 20 years after, or 15 years after a fire on Mount Lemmon outside of Tucson, and there's very little signs of regrowth of forest at all in this ecosystem. So in order to understand the future of fire, we need to understand the future of vegetation ecosystems in the Western United States. And this is really tricky business, much harder than just drawing a scatter plot and extrapolating out into the future. To try and address this, a team of my colleagues led by Winslow Hansen, who is a postdoc in my lab back at Columbia, has developed a forest ecosystem model for the Western United States. There are a lot of forest ecosystem models out there. Many forest ecosystems are built to work to operate at the scale of a landscape, say a few city blocks. Those models can simulate the behavior of individual trees, and they can simulate fire actually burning through vegetation in a very dynamic way where actual flames are being simulated. And then on the other end of the extreme are the global Earth system models that attempt to simulate forest ecosystem processes, but in an extremely coarse way, where a single grid cell might be something like 100 kilometers by 100 kilometers, and so there are a lot of simplified rules that go into those models. In this case, we've tried to come up with a compromise model that has a mid-level resolution that allows us to simulate complex forest processes, such as trees delivering seeds to nearby places, the storage of seeds in the ground, competition between seeds after a fire to determine which type of forest comes back, if at all, and how long that takes, and the maturation of trees to be able to produce new seeds after fires. So those are some of the complex processes we're trying to simulate, but at the same time, the model is simple enough to be able to run on a computer at the large scale of the entire Western United States. So while Winslow was building this model, I was working on building a statistical wildfire model. And we built these models talking to each other all the time, specifically so that these models could be coupled together, so that we can run fire simulations for the historical and future periods at the same time they're running forest simulations, so that our simulated fires can affect forest fuels, and the forest fuels can change as a result of the fires, and then those changes feed back to affect subsequent fire behavior that we're simulating. The fire model is a statistical one. We simulate clicker's messed up. Each month for each 12-kilometer grid cell across the Western United States, we simulate the probability that a fire is going to occur and the potential size of those fires. And these models are based on a number of variables, forest biomass variables, human population variables, and climate variables like the vapor pressure deficit and the frequency of wet days. Here now I'm just going to show you a couple slides to demonstrate that the forest fire model works pretty darn well. The orange record here is the same record of observed forest burned area that I was showing you previously in other slides. And then in gray are each of 400 different simulations. And then in black is the average of these simulations. Now, very importantly, what I'm showing you here are cross-validated results. And what that means is that for each consecutive, or period of 5 to 7 consecutive years, I withheld the data from those years and trained a new fire model using all the rest of the year data from the years besides those 5 to 7. I then used the climate and human population and forest data from those 5 to 7 withheld years to estimate what the burned area would be using the model that was trained on the rest of the data. I did that for each consecutive 5 to 7 year chunk. And so what you're looking at here in gray and black are estimates of fire activity in the Western United States that we call out of sample, meaning that those years were not actually used to train the data. And the fact that we have a really strong correlation here is evidence that our model at the scale of the Western United States works very well. But very importantly, this is a spatially explicit model. We're not just simulating the annual area burned for the entire Western United States. We're simulating individual fires at individual places. And so if we zoom in now on a more of a regional level, if I just split the Western United States into 4 different quarters, you can see that even at the regional level, we're generally doing pretty well at capturing interannual variability as well as the trend. We're simulating a large increase in area burned, similar to the one that has been observed. So how much of the observed increase in forest fire area does our model account for? Now I'm showing you a model results from a model that was trained on all of the data, and so observations are in orange, the model results are in black, and the difference or the similarity in trend lines indicates that about 3/4 of the observed increase in annual area burned in Western United States forests is captured by our model. One reason why we don't capture more of the trend is 2020. Our model has a very difficult time simulating annual areas burned as large as 2020. That tells me that we're probably missing something in the model. Obviously, we all remember 2020 was a pretty abnormal year. Climatically, it was a very abnormal year. There was a huge lightning storm that came across California as Tropical Storm Fausto broke apart in mid to late August of 2020. Lightning in California is very rare, and so there was a gigantic introduction of sudden fires during a heat wave in August of 2020, and people, or the fire suppression resources, were probably pretty limited, the way that pretty much every human system globally was very limited in the summer of 2020. There was then, in September of 2020, a record-breaking heat wave. You may remember, I think that was the heat wave where Death Valley hit 129 degrees Fahrenheit for the first time. That heat wave worked to reignite fires that had already spread a lot in August of 2020. And so 2020 was a very abnormal year in terms of the climate event, the lightning event, and in terms very likely of human fire suppression resources being limited and spread very thin by this sudden rash of hundreds of fires across Northern California and Oregon. Now, the model is probabilistic, and that means that every time we run our fire model, the results look different from the previous one. And so here's now a histogram of the trends that we simulate across 1,000 different model simulations, plotted as a function of the percent of the observed trend. So model simulations that have 100% of the observed trend are model simulations that show the Western U.S. burning actually as much as was observed in the last 40 years. And so on average, it's about 3/4 of the annual area burn of the observed trend that's captured by our model. But about 5% of the time, our model actually simulates trends that are larger than the annual area burn. The reason I show you this, or to show this wide variety of model simulations, is to say that the observed record that we've seen, the observed fire record that we've had play out over the last 40 years, probably didn't need to look the way that it did. There's a lot of room for natural variability, for randomness with wildfire. And given the same exact climate, the same exact human population, the same exact forest ecosystems, the observed fire record over the last 40 years could have resulted in a smaller trend in area burned or a larger trend in area burned. What that implies is that for the future, there's very likely a wide range of uncertainty in what is going to actually play out. What if human-caused climate trends had not occurred? What would have happened with wildfires in the Western United States? We can try and address this question by playing a counterfactual game. The counterfactual game we're going to play is one where we consider a hypothetical climate record where human-caused climate trends didn't occur, but the year-to-year variations in climate that were observed did. And so in black here, I'm showing you a record of March through October average maximum vapor pressure deficit, and this is the observed record. There was a trend in the vapor pressure deficit driven largely by warming of the atmosphere. The blue is now a counterfactual record where I've done my best to remove the trends that CMIP6 climate models say were due to human-caused climate change. Now, I'm not only removing the trends in the background mean state, but I'm also removing trends in the distribution of daily VPDs. And that is because climate change might affect VPD on cool days more than on warm days, or more on warm days than on cool days. And so here in blue, I'm trying the best I can to force the observed climate record to take on the daily distribution that climate models say was the daily distribution in the mid-1800s. We can do the same with other variables. I've done it. I did it with daily maximum temperature, daily minimum temperature, relative humidity, daily precipitation, daily wind speed, and daily solar radiation. Here's now a plot of the same thing for the summertime wet days. Black is the observed record, so we can see this decline over the last 40 years in the frequency of summertime wet days. And climate models say that without climate change, the summers would have probably seen a bit more wet days over the last 20 years than we observed. And so in both of these cases, climate models are generally saying that climate change should have promoted the conditions that cause fire over the last, or that lead to large fires over the last 40 years. And now I'm showing you the results of our fire simulations, forced in black with the observed climate data. This is the same record of observed, or of simulated burned area that I was showing you previously. And in blue is our record of fire simulated in this hypothetical world where we've removed human-caused climate change. What you can see is that the vast majority of the simulated increase in annual area burned over the last 40 years is driven by trends in human-caused climate change as expressed by the SINP6 models, but not all of it. Here, I'll talk about that more right now. So now I'm showing you that same histogram of simulated trends relative to the observed trend that I was showing you before, and now I'm showing you the second histogram of simulated trends in a world without climate change. And you can see that of our 1,000 simulations, all of them show somewhat of an increase in annual area burned, with the average simulation accounting for about 24% of the observed annual area burned. What this suggests is if we wanted to believe the SINP6 models and how they express the way that human greenhouse gas emissions change the climate, then we'd come away with the conclusion that even without climate change, we would have seen a moderate increase in annual area burned. Now, this could be that just suggesting that the models are not quite right. Certainly, SINP6 models have uncertainty in how they simulate the response of the climate system to greenhouse gas forcing. But it also does make some sense. Over the last 40 years, we've seen this general trend toward a colder state in the tropical Pacific, toward more La Nina-like conditions. This generally causes drier winters and springs in the southwestern United States and warmer, higher VPD temperatures across the entire western United States. And we have seen a reduction in specific humidity across the southwestern United States that actually is not simulated by models. Climate models simulate that as the globe warms, we get more water vapor molecules in the global atmosphere because of enhanced evaporation off the oceans. In the southwestern United States, in spring and summer, we've actually seen a decline in specific humidity. Very likely this is being driven by natural climate variability. And so natural climate variability has also loaded the dice with a little bit of bad luck if we consider large forest fires a bad thing. One of the values of doing these spatially explicit simulations rather than just the west-wide climate fire regressions I showed at the beginning is that we can then do simulations to try and understand where the anthropogenic climate change effect has been the strongest so far. And so what I'm showing you here, this is qualitative because the numbers are kind of hard to wrap the mind around. But what I'm showing you here is the average area burned across 1,000 different model simulations when we force the model with observed climate data, minus the average area burned across 1,000 simulations where we removed the climate change trends from the observed climate record. And so red means that climate change is simulated to have enhanced fire sizes dramatically. And we can see that some areas are redder than others. The general tendency is for the climate change effect on forest fire to be the most potent in the places that have a combination of two things: high fuel densities, relatively dry climates, so three things, sorry. High fuel densities, relatively dry climates, and Mediterranean-type climates. So areas like the West Coast, every summer is is pretty reliably dry. And so a record hot summer in a Mediterranean type climate is much more likely to lead to a record-breaking fire year than a record hot summer in, say, the Northern Rockies, where there is no real dry season. So in the Northern Rockies, a record hot summer could lead to the beginning of a bunch of fires, but rain could show up at any time to stifle those fires. And so it takes a lot more to get a record hot fire or a record-breaking fire year outside of the Mediterranean climate system than within the Mediterranean climate system. How has anthropogenic climate change affected our simulations of forest biomass? This is important because changes in forest biomass might feed back or should feed back to affect fire moving forward in the next few decades. And is this already happening? Is the growth or the emergence of gigantic megafires already removing enough forest biomass that forest fires are starting to not respond as potently to warming and drying of the air? So here are some high-level results of our simulations of forest biomass for the period of 1951 through 2023. In black is showing you change in forest biomass since 1951, simulated. And so you can see some slight declines in forest biomass up until the 2000s, and then forest biomass just starts tanking. According to our model, we've seen something like 1.75% decrease in total above ground live biomass in the Western United States. And then blue is showing you results from the same simulations, but in a world where we don't have the human-caused climate change. And we see that even in those simulations, the model is suggesting a slight decrease in forest biomass, but our model says that human-caused climate change accounts for about half of the half of the simulated forest biomass when we force simulations with observed climate data. And these reductions in forest biomass have some interesting spatial patterns to them. In general, the decreases in forest biomass that we simulate have been the strongest in California and the Pacific Northwest. Is this reduction in forest biomass due to warming, drying, and increased fire enough to actually start affecting the sizes of fires at the scale, or the annual acreage burned at the scale of the entire western U.S.? The answer is no, not according to our models. We can run a simple experiment where, in one case, we simulate the period of 1951 to present, where every year we hold fuels at the 1951 levels, where forest biomass was about 2% higher than it is today. And in the other, we can simulate the last 51 years, where the forest is forced to always look the way that we simulated it in 2022. And we see that, in general, the two sets of simulations look identical. That means that the 2% loss in forest biomass that we simulate over the last century is not nearly strong enough to, at the scale of the Western United States, start bending the curve on the increase in annual area burn. That suggests that we should expect annual area burn to continue increasing rapidly. And so I'm going to finish by just showing you some very preliminary results where we simulate forest fire and forest ecosystems all the way out to 2100. These are still kind of hard simulations to make. It is a pretty small scale operation. I do all my simulations on this computer here, for example. And so far we've only had time to run one simulation out to 2100. This particular simulation is is taking climate projections from one simulation from the CESM2 climate model. We start with the historical scenario that starts in 1850 and goes through 2014, and then it continues to 2100 under the moderate SSP 245 emission scenario. And so black is showing you the average of a bunch of simulations where our forest fire model and the forest ecosystem model are coupled together. And what we see is a continued absolute explosion of forest fire activity in the Western United States. Here in blue, I'm showing you the amount of forest fire area that was observed to burn in the current record year, 2020. In this simulation, by the 2030s, we're seeing this, the current record getting shattered and shattered again, then the 2050s shattered again, where we actually do have a year here where 10% of the forest area burned in the Western United, or forest area in the Western United States is burning. And you might ask, well, well, shouldn't we at some point be running out of forest fuels to support these giant fires? And the answer is only kind of. We can address that question by running the same experiment again, but where we don't have forest fire and forest ecosystems coupled. That is, the forest ecosystem always stays the same as it was in the in the last few decades. And in that simulation, we see that the biggest fire years are about 20% larger. And so what this says is that the response of forest ecosystems and the simulated reduction in forest biomass does reduce the response of forest fire sizes a little bit in our simulations in the second half of the century, but we still see these repeated occurrences of gigantic forest fire years playing out through the rest of this century. I don't have simulations forced by other climate models, but I suspect that the story is going to be more or less the same. One really important thing, though, that I suggested at the beginning of the talk is that forest fire area is not necessarily the most important thing to focus on. Fire is not inherently a bad thing. Large fires aren't inherently a bad thing. But in some forest ecosystems, very large, severe fires are a bad thing. Fires that emit huge amounts of smoke pollution and PM 2.5 are a bad thing for human populations across the country. Fires that are burning very fast and very energetically and smashing into towns are obviously a bad thing for people living in those towns. There are other things that we should care about more than just forest area burn. And so in addition to being able to simulate forest area burned accurately, it's also very important that we can simulate other things like the severity of fires, the carbon emitted by fires, and we're getting there, I believe. And in this plot, well, first over here I'm showing you our simulated reductions or simulated changes in forest biomass by the end of this century, comparing the end of the 21st century to the end of the 20th century. And we're seeing really large decreases in forest biomass. And so even though our simulations are showing or projecting continued occurrences of gigantic fires and record-breaking years in terms of area burned, what I'm showing you here now is an actual reduction in the concentrated intensity of fires. I'm showing you the total biomass combusted per acre or per hectare burned. And so we are going to, according to these simulations, see this gigantic increase in total hectares burned, but the amount of biomass combusted per hectare burned actually goes down in our simulations over the rest of the century. And so it is through the reduction in biomass that we're seeing these projected decreases in the intensity of fire in any individual location within a fire. And so there is potential for us to do things like fuels treatments and large prescribed fires to reduce fuel densities even more, to not necessarily have a meaningful influence on the size of fires, but we can have meaningful influence, I believe these simulations are suggesting, on the intensity of fires and therefore the unwanted consequences of some fires. With that, I will conclude by just reiterating that climate trends have dictated that we've seen an explosion in the sizes of fires in the Western United States, especially in forests. We project that to continue for the rest of the century. Humans are very likely to be increasingly in harm's way. People keep moving into the Western United States and they're preferentially moving in flammable areas. And so even though fire isn't necessarily a bad thing, these model simulations can be used to hopefully guide responses in terms of treating fuels or changing fire suppression strategies that can minimize the harm done to human populations and to some ecosystems in the Western United States. But it's very unlikely that we're going to be able to have much of an impact on the growing sizes of fires themselves. With that, I am all finished, and thanks for your time.
Thanks for a great talk. You focused on like the atmospheric conditions, VPD. You haven't talked about insect damage and beetle kills and stuff like that. Is that in the model? And if not, how would it affect your projections?
Yeah, the question is, do we involve other mortality processes in our modeling, specifically bark beetles? And the answer is no. Our model does have trees die or have a higher probability of mortality as a result of drought, but we don't have beetles in here yet, but we will. Bill has a relatively simple insect model in his modeling. I've got some ideas about how to do that as well. The question then is, do have the big mortality events that we've observed in the last few decades due to bark beetles actually had much of an influence on forest fire? And my answer is going to be relatively simple. It is like, first, we'd kind of expect that we would. If you kill a bunch of trees and reduce forest biomass, then you might expect that the subsequent fires would have a lower probability of burning through those recently killed areas with very high intensity. And the data just don't really bear that out all that much. It seems a lot more complicated. Modeling suggests that in the year or two immediately after a big mortality event, when the needles are still on the trees, then the probability of having a really high intensity fire fly through that area goes up. But then afterwards, once the needles fall to the ground, the way that air circulates through the stand of snags actually causes fire intensity to go down. But I could be totally butchering that. I admittedly don't know a whole lot. But I do, in trying to understand what the carbon dynamics over the next century look like, I think it's really important to have some representation of beetles and other disturbances. But at the same time, I don't have a whole lot of confidence that we're going to do that all that well. Beetles are super complicated. Yes?
Speaking of carbon dynamics, just thinking about kind of the net carbon stored in our western forests over this period of time you've been modeling. You didn't necessarily present that exactly, but my sense from what you were saying is that we are going to see a net overall loss of carbon from western forests because those fires are slowly going to reduce the amount of biomass that we have stored there. Is that an accurate interpretation?
Yeah, that is. What I was showing you was our projections of above ground live biomass, but if we look at above ground dead biomass, we see the same thing. We're not simulating anything below ground. And a huge caveat is that we're also not simulating the effect of increased CO2 on forests. And so in climate model world shows above ground biomass increasing across the western United States because of CO2 fertilization. But these Earth system models aren't very good at doing things like wildfire. And one of the things that our modeling shows is that increased biomass leads to increased probability of large wildfire. And so if we do end up seeing big increases in growth rates, above ground growth rates because of increased CO2, that may actually load the dice toward bigger drops in biomass due to high intensity wildfires. I think that the role of CO2 fertilization in the carbon and wildfire story for the Western United States is a source of huge uncertainty and really interesting to think that potentially increases in biomass due to CO2 in the short term could lead to decreases in net biomass in the long term.
There's a big water limitation factor involved there too.
Agreed.
Their ability to take advantage of that CO2 emission.
I agree with that, and as far as I can tell, the Earth system models disagree with that. And so I have a tough time really trusting the Earth system models because my experience in the real world says that drought sensitivity in the western United States forest is just really, really high. Yes?
So I have a question going back to the poster showing at the very beginning where it was the largest fires, like the 10th or the 90th percentile fires that were seeing the biggest increases. Do you have a sense of why that would be the case? Is that related to, once the fire gets so much pressure and some size, it just becomes, it basically grows exponentially. Is the fire answer interactions of those playing a role into that? They're more impactful and fires changing meteorology. Do you think that's playing a role in these bigger fires?
I think there are a lot of things that could be changing playing a role. What you just suggest about fires actually promoting their own growth by changing meteorology is an interesting one that could be at play. But I think the main thing going on is simple geometry. That so a circle, as we expand the radius of the circle linearly, then its area is going to increase exponentially. As we increase the length of a fire line, the potential for that fire line to spawn future fires ahead of it increases exponentially. And so if we just were to scatter a whole bunch of fires across the landscape and give them a normally distributed random ability to grow in size, or to grow, then because of the geometric exponential response of size to linear increases in radius, we'll see the fire sizes take on an exponential distribution, even though they were given a normal distribution of the ability to grow at the beginning. But because bigger fires have a greater potential to grow large than smaller fires do, we end up with an exponential distribution of individual fires. If we then tell all of the fires, you're now in a warmer and drier environment, we want all of you to become larger. It's the biggest fires that have the biggest potential to grow, and the smallest fires that have the smallest potential to grow, and so you end up with is an exponential response in the mean fire size. We've played a bunch of numerical games where we instead of taking each individual fire size and summing up to get the total annual area burned, we assigned each individual fire a quantile and summed those up in a given year, and then plotted the annual summed fire size quantile versus VPD, and the relationship becomes perfectly linear. And so the exponential response of fire sizes to annual area burned appears to be driven by the exponential distribution of individual fire sizes. Yes?
Let's do one last quick one.
So you I don't know if this is quick. You alluded to the effects of CO2 on the carbon amount of the forest, and the CO2 radiative effect is obviously going to be a big driver of the changes in VPD that you're seeing through the temperature. It's also going to have a big impact on latent heat fluxes from the surface, both by changing your ET rates because of effects on stomata, and I'm curious if you've accounted for that in your fire model, like if you run it with like the C-format VGC simulation or something and seen if that has an impact. And also if your changes in forest, if they're big enough to be influencing VPD themselves, like you just burn down a huge area, is that going to impact the VPD in a way that's going to propagate the VPD in the next years that will impact forest?
Yeah, thank you. The answer is no to all of that. So the question is basically, what's the role of land atmosphere interactions here? Fires actually change the climate conditions in an area, and carbon dioxide is changing the way that in model world, the productivity of plants and the rate at which plants are allowing water to transpire through the stomata. This all affects the climate environment that could promote or suppress fire. If models are not accurately simulating things like water fluxes from the soil to the atmosphere and how those respond to increases in CO2 and changes in climate, then very likely models are also not simulating things like extremely high VPD days. Maybe models are underestimating them, or maybe models are overestimating them. There's uncertainty in how in the future of land-atmosphere interactions. This is your question is totally in line with the long conversation I was having with Chow earlier yesterday. How we think there's actually a whole bunch of extra uncertainty in the future of fire because of uncertainty in how models simulate the way that extreme heat and aridity events respond to drought. But we haven't addressed any of that yet.
Please come up and talk to Park after if you're interested. And thank you.